Hello and welcome to this video on the remainder theorem. This video might be a little lengthy because I'm trying to give a decent explanation of the theorem. So I'm going to give a quick explanation and demonstration and show two applications. The first application is just asking what is the remainder of a given division, and application two is the given binomial a factor of the given polynomial. So if you want to look right here at these time signatures, okay, you might be able to fast forward to a part that you'd like to see or not. Feel free to watch the whole thing, obviously. So let's get cracking. Okay, so the remainder theorem, if I give a quick explanation of it, it says when we divide a polynomial that I'll call p of x by a binomial of the form x minus a, then the remainder will be p of a. Okay, well, that doesn't seem too thrilling, but let's try and drill down into it and see what it says a little bit more. Okay, it says if you take the number a and actually evaluate it in the function, okay, it will give you the remainder. Now, where does that a come from? It just comes from the binomial that's of the form x minus a. Okay, so let's see this in action here. And I'm not going to ask a particular question. I'm just going to kind of like play with the theorem and put it through its paces, sort of. So if I had 2x squared minus x minus 15 divided by x minus 1, and I actually did that division out using a long division algorithm for polynomial division, okay, I would in fact, on the bottom line, get a remainder of negative 14. Okay? So by the remainder theorem, though, it says I could have gotten that negative 14 a different way. And let's take a look at that. Well, if I call this p of x, the expression 2x squared minus x minus 15, and I call this x minus a over here, the expression x minus 1, I can see that by that model, a is going to be equal to 1. So the remainder theorem says to take the value from the binomial and evaluate it. So I'm going to do p of 1. I'm just going to plug it in here to p of x and do 2 times 1 squared minus 1 minus 15. And then quickly through the order of operations, I'm simplifying. This line I get 2 minus 1 minus 15, which is in fact 1 minus 15 is negative 14. So what did I do here? I actually got the remainder without doing any division. Okay, now that might not seem special, but remainders are very important in different things in number theory, so it's good to be able to examine this. Again, over here, using polynomial long division, you notice I get more than the remainder. Down here, I actually get the result of the division. And I could say what the answer to the division is, but the remainder theorem focuses squarely on the remainder. Okay, so let's take another look at another sort of demonstration of this. And we'll take a look at this expression here where it says 2x cubed plus 3x squared minus 17x minus 30, all divided by x plus 2. Well, if you see if I do this out by long division, even if you're not familiar with long division, you should be able to trust me that I did long division here. You see that on the bottom line I get a remainder of 0. Okay? Well, using the remainder theorem, we should get the same thing. So I'll call this expression here the polynomial p of x, and I'll call this binomial x minus a. But I hope you notice here that the binomial is given as a sum. So I'm just going to rewrite it as a second by x minus negative 2, which is obviously the same as x plus 2. Hopefully this gives you clarity that a is really equal to negative 2. So moving on from there, I will in fact evaluate p of x for an input of negative 2, which is just do p at negative 2, which says to do 2 times negative 2 cubed plus 3 times negative 2 squared minus 17 times negative 2 minus 30. And then decently quickly by the order of operations, I'll simplify this expression, and you'll see that I in fact get negative 16 plus 12 plus 34 minus 30. Well, you'll see if I just do a little associative property here, I get -4 first two terms and +4 for the next two. So that is in fact equal to 0. Again, I'll try and highlight this with the magic pen. Notice that I got the remainder without doing division. So it's kind of a neat concept. You're finding a remainder of a division without doing the division. Okay? And you see my remainders in fact match. My remainder here is in fact 0. Okay. So I haven't really asked a question yet, so I'm going to do that in the next two applications now that you see how this theorem works. Okay, so if you fast forward to this part, it assumes that you kind of know how the remainder theorem works. So I'm just going to apply it here. And in this question, it's just to say, what is the remainder? So what is the remainder when we divide -3x cubed plus 4x squared minus 17x minus 20 by x minus 7? Okay, well, by the remainder theorem, I'll call this p of x, and my binomial I'll label as x minus a, making a obviously 7. So the only thing I need to do is p at 7, which is -3 times 7 cubed plus 4 times 7 squared minus 17 times 7 minus 20. And then through the magic of fast forward, just going through a little bit of the order of operations here, showing my work, but pretty academic at this point, we get -972. So I just wanted to show you that you should kind of show your work on a problem like this, but we understand what that work will look like. Okay, so the remainder here is in fact -972 when you do the above division. Okay, so all it asked for was what was the remainder when you do the division. Again, pretty clever that you're finding the remainder without actually doing division. So, excuse me. Okay, sorry, a little technical difficulty there for a second. Sorry for the lag. And this takes us to application 2, if you've just fast forward here. And it asks, is the given binomial factor the given polynomial? Okay, so there's a little bit more of a theoretical question here. But you shouldn't be intimidated by it because it carries over from something you learned a long time ago. And I'm just going to go there for a second. Okay, so it says, so let's talk about a basic idea of remainders for a second, okay? Is 16 a factor of 48? Well, you should know it is, but why? Because 16 goes into 48 3 times, and when you do that, there is, in fact, no remainder. So there's this relationship between something not having a remainder when you do its division and it being a factor. Well, is 24 a factor of 52? It's not. Well, you could sit there and say, well, it doesn't go into 52 evenly, but more specifically, when you do the long division of it, you do get a remainder. So what does that mean? It means pretty basically that when the remainder of a over b is 0, then b is a factor of a. So we're just going to apply that idea, something you've known all your life, and just realize if you get a remainder from a division, then the divisor is not a factor of the numerator, and vice versa. So let's take a look here. And these questions ask, is the given binomial factor of the given polynomial? So without doing division, I'll just do this by the idea of its remainder. Okay, I'll call this p of x, and I'll call this x minus a, but again, it's going to need to be x minus -3. Okay, in this problem, so now I will evaluate p at -3, which gives me 2 times -3 squared plus 5 times -3 minus 3, which is going to give me 2 times 9 minus 15 minus 3, which is 18 minus 15 minus 3, which is equal to 0. Now, the way we answer is it says because the remainder is 0, okay, then x plus 3 is a factor of 2x squared plus 5x minus 3. That's the appropriate way to answer this, kind of with a full statement. It'll really help harness your understanding. Okay, and so in this next example, where it says is x minus 1 a factor of negative 2x cubed plus 5x squared minus 3, I'll call this polynomial p of x so that I can follow the model in the theorem. I'll call this binomial x minus a, therefore a equals 1. I will now do p at 1, which is usually a very easy evaluation to plug 1 or 0 in for something. In this case, I'm plugging in 1, obviously. So 5 times 1 squared, continuing with the evaluation writing. This gives me negative 2 times 1 plus 5 times 1 minus 3, which is equal to negative 2 plus 5 minus 3. So we have here that this is in fact equal to 0. Therefore, that's the remainder. And we have that, if I just extend the page here, x minus 1 is a factor of negative 2x cubed plus 5x squared minus 3 because the remainder is 0. Okay? Good way to answer that. Okay, I just want to do one more example here to kind of round this series of examples out. It says, is x minus 4 a factor of 7x squared minus 20x minus 3? And again, if when we did a division of this polynomial by x minus 4, if there were no remainder, then obviously it goes into it evenly, so it would be a factor. Okay, so again, I'm circumventing the whole division process by just doing the remainder theorem because that's all I'm really interested here. It's a great application for it. So I'll call that expression p of x, and I'll call this expression x minus a, which makes a equals 4. So I just need to do p of 4 and see that that is equal to 7 times 4 squared minus 20 times 4 minus 3. And then by the order of operations, we get 7 times 16 minus 80 minus 3, which is equal to 112 minus 80 minus 3, which is going to give us 29. Okay? So I did not get a remainder of 0. This means that x minus 4 is, sorry about that, my phone rang. So we have that x minus 4 is not a factor of 7x squared minus 20x minus 3 because the remainder is not equal to 0. So that's the appropriate way to answer that. Okay? So I hope that this was informative for you and took you through the paces of what the basics of the remainder theorem are in terms of its mechanics. Again, it talks about getting a remainder without actually doing division, which is kind of cool. And then there's a couple of applications, which are just, could you tell me the remainder of this division without doing the division? And can you tell me if a given binomial is a factor of a given polynomial? So feel free to watch again. Enjoy. Always practice hard.